Welcome back to All This Math. Make sure you subscribe to the channel. Make sure you share the channel with other people as well. Today we're going to work on some probability tree diagrams. All right. As you also see, I have one of my Cheney University hoodies on. Cheney is the school where I teach at. Cheney is the first historically black college university, even though it wasn't the first to grant college degrees. Lincoln University was the first to grant college degrees, even though Cheney was established in 1837 as the Institute for Colored Youth located in South Philadelphia. So it was the first institution, but back then it was more so a high school, even though it was very rigorous, right? It wasn't granting college degrees. Lincoln was the first to grant college degrees. All right. Back then, when it was the Institute of Colored Youth, they had, instructors such as the late Octavius Cato, who some people say Cato. I'm not sure what the correct pronunciation actually is. But there's a statue of him in Philly outside of City Hall in Center City. He was a math instructor. He was also a great baseball player, also a civil rights activist. He stood on stages along with Frederick Douglass and helped to recruit soldiers for the Union Army during the Civil War. Later was assassinated by some racist white boy from South Philly in 1870 after the 15th Amendment, which granted black suffrage to black males. After that amendment to the Constitution was passed, the 15th Amendment, he was assassinated. And he had one of the largest funerals in the history of the United States up to that point as a result. So yeah, just a little bit of history about Cheney University before we get into this math, because that's what we do here on this channel. We provide math lessons infused with black history and black culture. So go do your research on historically black colleges, Cheney University, Lincoln University, Octavius Cato, also Fannie Jackson Coppin. While Octavius Cato was an instructor at Cheney University, well, at that time it was called the Institute for Colored Youth, Fannie Jackson Coppin was the principal essentially, or the president of the college, if you will, or the provost maybe at that time. So definitely research Fannie Jackson Coppin. Also, if you're out in Baltimore, or even if you're not in Baltimore, check out her connections to Coppin State University or Coppin University in Baltimore. All right, now let's get into this problem. So this is a word problem that we're going to be doing. I didn't write it on the board, right? It'll be in the description section underneath of this video, right? But I'm going to read it out loud, and we're going to document some of the information on the board. All right, so it kind of starts like this. Jakisha has a bag of Jolly Ranchers, right? Jakisha has a bag of Jolly Ranchers. So originally the problem was talking about the color of the candy, but I kind of remixed it a little bit. So Jakisha has a bag of Jolly Ranchers with 7 blue raspberry candies and 3 watermelon candies in it. All right, so we got blue raspberry and we got watermelon. Those are the 2 flavors. All right. She picks a piece of candy at random from the bag, replaces it. That's important. Make sure you make a note of that. She replaces it because probability problems with replacement versus problems without replacement are done differently. It changes the numbers drastically. So when you're looking at a probability problem and somebody pulling marbles out of a bag, somebody pulling candy out of a bag, somebody pulling dice out of a bag, or whatever they're pulling out of a bag, for selection, and you're trying to, figure out what the probability is of getting a certain number or a certain color or whatever. If there's replacement, that's going to affect your math. If there's not replacement, that's also going to affect your math. So basically, pay close attention to that, if there's replacement or not. In this problem, there is replacement. So every time she pull a candy out the bag, she's not going to eat the candy, right? Because she's replacing it. You know what I'm saying? So she's going to take a piece of candy out the bag just to see what she gets. And then she puts a piece of candy back in the bag. All right, so it says she replaces it and then picks again at random. So that means she's picking 2 pieces of candy. All right, so understand, like I tell my students, you got to be able to read first before you even get into the math. You got to read first and then do math. That's why reading and math really go together. So really shouldn't be no conversation about being a reading person versus being a math person, right? We got to get rid of that because that stops a lot of people from understanding math, because a lot of the issues with math are math word problems, our inability to understand math word problems. And a lot of students don't understand math word problems because they lack the reading comprehension. So, but they're sitting there like, oh, but you're in a math class, so so it's a math issue. A lot of times it's not a math issue. So we got to combine the reading comprehension with mathematical comprehension. We got to combine them, and we got to read first. All right. Then she picks again at random. So she's picking 2 pieces of candy, right? She picks a piece, replaces it, throws it back in the bag. Then she picks another one. All right. So our instructions are to draw a tree diagram to represent this situation. and use it to calculate the probabilities that she picks 4 things. So 4 things. So the first thing, what's the probability that she picks 2 watermelon candies? All right, so she digs in the bag, she pulls out a piece of candy, puts that piece back. Then digs in the bag, pulls out a piece of candy again. What's the probability, the statistical probability that she's gonna pull out 2 watermelon candies? The next thing we're gonna try to figure out, what's the probability she don't pull out no red candy? She don't pull out no watermelon, rather, right? Neither of those pieces of candies are watermelons. Third scenario, what's the probability that she pulls at least, that's an important word you need to understand in mathematics, at least. How do we represent that mathematically? At least, right? At least 1 blue raspberry, meaning she could pull out 1 blue raspberry or she could pull out 2 blue raspberries. What's the probability of those things happening? And also fourth, what's the probability that she pulls out 1 candy of each flavor? So one watermelon and 1 blue raspberry. All right, so check this out, right? Let's draw a tree diagram. Tree diagrams are very helpful because they give a visual explanation of what's happening. You get a visual, you get a picture. You know what I'm saying? Like, you know, like I said, a picture's worth 1,000 words, right? So in math, a lot of times people don't understand because they see equations, they're given equations and formulas, and they don't get to see the picture. They don't get to see the big picture. So some people understand better when they see the picture, you know, just like on certain social networks, you can understand the situation better, understand a meme or whatever because of the picture. The picture helps you to get a better understanding as opposed to somebody just telling you or typing about it. You know what I'm saying? So let's draw the tree diagram. All right, so the tree diagram, all right, it's going to look like this, right? And the tree diagram is going to represent all the possible outcomes in this scenario. So for our tree diagram, we're going to call the blue raspberry candy blue, and we're going to call the watermelon candy red. We're going to use blue and red. We're going to keep it simple, blue and red, all right? So we first start out with a sideways V, all right? We're going to represent our first 2 branches, all right? So we got so think about a tree, right? You got a tree, measure at a tree, and then trees have branches. And then sometimes those branches have branches. And branches just keep growing. Like I think about it in terms of like my first job I ever had, I was 15 years old. I worked at the Enoch Pratt Free Library in downtown Baltimore on Cathedral Street. That was the main library, right? We called it the main branch, but that actually doesn't really make sense because it really was the trunk of the tree if it's the main library, right? So we got the main library, and then the main library has different branches in different parts of the city. Like, so I grew up in the area near Northwood, right? So I would go to the Northwood branch of the library sometimes, right? To do like projects and get books and whatnot when I was a youngin'. Other times I would go to other libraries. I can't even remember what some of the other branches were, but I'm saying that to show the point for you to start thinking about like what it looks like. What do we mean when we talk about branches? So let's start here, and then these are our first 2 branches, all right? So this represents Jakisha, because remember, we're talking about Jakisha in this problem, right? Her pulling out a red candy or her pulling out a blue candy. All right, so this is how we set up a tree diagram. So we got 2 scenarios, right? 2 options. There's only 2 options. It's not 3 options. There's only 2 options. If it was 3 options, then we'd have another branch. But it's only 2 options. So she can either pull red candy or blue candy, red candy or blue candy. So you got to read the problem and understand what your options are. Once you understand what your options are, that helps you to start your tree. All right. Now that represents the first piece of candy. So what I'm gonna do is I'm gonna write first candy. All right. Then we're gonna do another branch from the red candy and another branch from the blue candy. That's gonna look like this. So another red, another blue, another red, or another blue. So this is the second candy. All right. So now, then we're going to have a column. Then this is how I suggest you set these problems up. So this branch right here with these 2 branches represents the first time she digs in the bag and pulls the candy out. These 2 branches right here, well, these 4 actually, 1, 2, 3, 4, represents the second time she pulls a piece of candy out. All right. Then we want to talk about the potential outcomes, right? We want to list and just simplify in a simple way, list the potential outcomes. So I'm going to have an outcome column. And then after that, I'm going to have a probability column. Oh, here we go. Follow us on Instagram too, because we got content on Instagram also. So follow us at All This Math on Instagram too. All right, so what does that mean, the outcome? All right, this is what it means, because it might be confusing, right? And it makes sense if it's confusing. Don't feel bad. So we start here. She digs her hand in the bag of Jolly Ranchers. She pulls out a red candy. Well, a watermelon candy. Then she pulls out another watermelon candy. That's one outcome, one possible outcome. So we're going to call that RR. Boom, RR. Because she pulled out a red and another red. So we call that red, red. That's what we call that. Then we're going to do the same thing for this. So how do we get here? We start here. She pulls out a red first. Then she pulls out a blue. We're going to call that RB. Because she went to a red, then she went to a blue. So we call that RB. So you seeing the pattern now? You're probably starting to see the pattern now. So what are we going to call this one? She starts here. She pulls out a blue. Then she pulls out a red. We're going to call that BR. Then we go back here. Go into the bag. She pulls out a blue. Then she pulls out another blue. We call that BB. So 4 possible outcomes in this problem. There's 4 possible outcomes. She could pull out 2 reds. She could pull out a red, then a blue. She could pull out a blue, then a red. Or she could pull out a blue, then a blue. All right? Now we're going to figure out the probability of each of these things happening. And then once we know the probability of each of these things happening, we're going to go back to the 4 scenarios from the problem. And then we're going to figure out the statistical likelihood or the mathematical probability of each of those things happening, answering those questions. All right. Now, to pull out a red candy and a red candy, when we say the word and in probability, that indicates multiplication. You should write that down in your notes. When we say the word and in probability problems, that indicates multiplication. When we say the word or in probability problems, that indicates addition. You should write that in your notes too. So, and it might be confusing because usually in mathematical word problems, the word and indicates addition. But think about it this way. Multiplication is just repeated addition anyway. So they're very much related. So when we're dealing with probability, remember, when we're dealing with probability, the word and indicates that we're doing multiplication. The word or indicates that we're doing addition. All right, so watch what happens. So this outcome is pulling a red candy and a red candy. But before we even do the probability of the scenario, let's go back and do the individual probabilities of doing each thing. All right, so the individual probability of, let's say, of just pulling a red candy. What's the individual probability of pulling a red candy? How do we figure that out? We go back to the word problem and we find out all together how many pieces of candy are in the bag and then how many red candies are in the bag. So if we go back to the problem, it says Jakisha has a bag with 7 blue candies or 7 blue raspberry candies and 3 watermelon flavored candies, right? That's all the candy she got. So all together, she got 10 pieces of candy. How do I know that? Because 7 plus 3 is 10. That's going to be my denominator in my individual probability or the likelihood of her pulling out a red candy. That's going to be my denominator. So the total amount of candy is your denominator. Then the actual type of candy that you focused on, how many pieces of that are in the bag? There are 3 of those. So that's going to be your numerator. So that means there's a 3 out of 10 chance she's going to pull a watermelon or a red candy. It's a 3 out of 10 chance. Again, why is it a 3 out of 10 chance? Because it's 10 pieces of candy altogether and it's 3 red candies. So it's 3 out of 10. So you should write that right here. So we actually should write, and you know what I'm going to do? This is looking a little drab, a little monochromatic. So let's do red. Let's do the probabilities in red. So the probability of pulling out a red piece of candy is 3 out of 10. All right. Now it's going to be the same all over this diagram. It's going to be the same all over this diagram, right? You know why it's going to be the same? Because there's replacement. This is where the point about replacement comes into play. Because since she's replacing the candy, she's putting it back in the bag, the probability is not going to change. Because since she's putting this piece back in the bag, that means it's still going to be 10 pieces of candy in the bag. And it's still going to be 3 red pieces of candy in the bag. Now, if she wasn't replacing it, that would change the next probability. You know why? Because if she take a piece of candy out of the bag and it used to be 10 pieces in there, now it's only 9 left. Because she took 1 out, because 10 minus 1 is 9. So it's only 9 pieces left. So then if you say, well, what's the probability of her pulling out another red candy? Now your denominator is going to be 9 because there's only 9 pieces of candy left. That's if she did not replace it. If she did not replace it. So that's why I said earlier, pay careful attention to if there's replacement or not replacement. Because if it ain't no replacement, then your denominator is going to be a 9. Also, if she already pulled out a piece of red candy, if at first there was 3 pieces of red candy and she took one out and didn't put it back, now it's only 2 pieces of red candy left. So that means your probability would be, if that was what this problem was saying, it would be 2 ninths. So you see how it would go from 3/10 to 2 ninths. But because she's replacing every piece of candy, the probability not going to change. You know why? Because if she takes out a red piece of candy when it was 10 pieces, and it was 3 pieces of red candy, 10 pieces altogether, and 3 pieces of red candy, and then puts it back, now how many pieces of candy are there? It's still 10 pieces of candy altogether. And it's still 3 red pieces altogether. So the probability is still 3/10. So you're going to write 3/10 for this problem because in this problem, she's replacing the candy. She ain't eating it. She's actually replacing it. She's putting it back. All right. So we're going to put 3/10 again. And actually, wherever you see an outcome of a red candy, we might as well just put 3/10 because that's not going to change. So here, here, and here, 3/10. All right. What about the blue raspberry? It was 7 blue raspberries. It was 7 pieces of blue raspberry candy, and it's 10 pieces altogether. So wherever you see the blue, like here, here, and here, we're going to put 7/10. So we're going to do 7/10, 7/10, 7/10. All right. So that's all our probabilities. So now check this out. What we're going to do next is we're going to figure out the probability of these outcomes. So what's the probability of pulling out a red piece of candy and another red candy? I use the word and. That means multiply. That means multiply. So the probability of pulling red is 3/10. The probability of pulling red again is also 3/10. So that means we're going to do 3/10 times 3/10. So this is where we need to know how to do multiplication of fractions. We need to know how to add fractions and we need to know how to multiply fractions. All right. I can't cross cancel. I like cross canceling, but I can't do it here because nothing diagonally has a common factor besides 1. That's why I can't do it. So I just multiply horizontally. 3 times 3 is 9. And I meant to switch back to the color black, but this is cool. 10 times 10 is 100. So there's a 9 out of 100 chance of this happening. That's kind of slim. If I convert this to not a decimal, but a percentage, well, I guess it is a decimal, then I convert that to a percentage. This will be 9%. So it's a 9% chance that she's going to pull out 2 red candies. That means it can happen, but it's a slim chance it can happen. It's not very likely, all right? That's why we study probability to find out the likelihood of something happening. Because if you know how likely it is for something to happen, then you know how much to bet if you wanted to bet. Like, what's the bet? Like, should I bet on that happening? Because if it's not that likely of it happening, then it probably won't happen. At the same time, if it's something rare and you're trying to come up, then if it's something rare, it's probably going to pay out more, because it was rare. All right, so 9%. Now let's find out what's the likelihood or the probability of pulling out a red candy and then a blue candy. That would be 3/10 times 7/10. So we do 3/10 times 7/10. Multiply those, we can't cross cancel, 21 over 100. Now don't forget, when you multiply, you do change the denominators. When you multiply fractions, you actually do multiply the denominators. When we add or subtract fractions, the denominators don't change because we would be trying to figure out how many of that denominator we have all together. So if it was like 2/3 and 5/3, we want to know how many thirds we have all together. So that's why we don't add the 3 and the 3 and make 6 in the denominator, because then you know how many sixths you have. We don't care about how many sixths we'd have. We want to know how many thirds we would have. So basically, I'm saying that to say, as a reminder, real quick reminder, when you add or subtract fractions, you don't change the denominator. When we multiply fractions, we change the denominators. We do 10 times 10 to get 100. So this is 21 hundredths. This is the same thing as saying 21%. So there's a 21% chance that this could happen. All right. Now, what's the likelihood? What's the probability of pulling out a blue and then pulling out a red? And you also see like why tree diagrams can be helpful, because you kind of can visualize, okay, you start here, put your hand in the bag, pull out a blue. Then from here, pull out a red. So it's a 7/10 chance this could happen. Then it's a 3/10 chance that could happen. So you just multiply these two numbers together. You get to kind of really just see what's happening. Like you see it through the tree diagram. So we do 7/10 times 3/10, which gives me, again, 21 out of 100. Which should make sense because this is really the same as this. It's just in a different order, right? And in this case, a different order is counted as a different scenario. All right, so that's, again, 21%. All right, so now, what's the probability of pulling out a blue and another blue? So blue raspberry and another blue raspberry. 7/10 times 7/10, because I said and, right? So 7/10 times 7/10. 7 times 7 is 49. 10 times 10 is 100. If I convert it to a percentage, that's just 49%. Now, how am I converting these to percentages? I just do the math. I do 9 divided by 100. I get 0.09, and then I move the decimal point 2 spaces to the right. Or I leave the decimal point there and I move the digits 2 spaces to the left. I still get 9, the whole number 9. 21 divided by 100, same thing. Do the math, you get 0.21, then you do 0.21 times 100, you get 21%. Same thing here. 49 divided by 100 is 0.49. 0.49 times 100 is 49. All right. Now, another thing about probabilities, one way to check your work is that when you do probability and you have different scenarios, all of your probabilities should add up to 100%. Or if they're in fraction form, they should all add up to 1. So 9 plus 21 is 30. 30 and 21 is 51. 51 and 49 is 100. So that's 100%. So we good, right? In fraction form, 9 and 21 is 30. 30 and 21 is 51. 51 and 49 is 100. 100 over 100 is equivalent to 1. Because anytime you got a fraction where the top number is the same as the bottom number, that fraction is equal to positive 1. Excuse me. So now we know all our probabilities for each of these scenarios, right? All the possible scenarios. So now we go back to the problem, right? We go back to the problem, and now we say, all right, the first question says, what's the probability of her, Jakisha, pulling out 2 watermelon flavored candies? All right, so look at our outcomes. 2 watermelon, so this is 2 watermelon flavored candies, right? This is not, so this don't count because this is red and blue. This is not because this is blue and red. This is definitely not because this is 2 blues. So the only scenario where she pulls out 2 red flavored candies or 2 watermelons is this one. So all you gotta do is go to this right here and say, oh, 9%. It's a 9 out of 100 chance that that's gonna happen. So the correct answer for letter A is 9%. So I'm gonna write that over here. 9%. That's the correct answer for letter A. Because the question says, what's the probability that she picks 2 red candies? This is the scenario where she picks 2 red candies. Not this one, not this one, not this one. Now, letter B. Letter B asks, what's the probability that she picks no red candy? No red candy. So that means it cannot be this one, because here all she picks is red candy. It can't be this one, because she picks a red candy. It can't be this one, because in this one she picks a red candy. It could be this one. This is the only scenario where she picks no red candy. She picks 2 blue raspberries. So there's a 49% chance of that happening. So let's go over here. So that's the answer. Excuse me for my allergies. Giving me some problems right now. Anyway, there's a 49% chance, or 49 out of 100 chance that she picks no red candy. No red candy. So, and again, that's another benefit of the tree diagram, because if you lay out your outcomes, your probabilities right here, corresponding to your outcomes, then when it comes time to answer the questions, all you got to do is read the question and then check, okay, which one am I talking about here? Now, part C says, at least 1 blue candy. At least. All right, at least. Now, she picked 2 pieces of candy. So when we see the phrase at least, we got to know how to utilize that. We got to know how to apply that, right? So at least means she could pick 1 blue raspberry candy or 2 blue raspberry candies. Now, notice I just used the word or. Notice that. And what I told y'all before, when we see the word or hear the word or, that means we're doing addition. we're going to add the probabilities together. We're not going to multiply the probabilities together. We're going to add the probabilities together, right? So we look for the outcomes that include either one blue candy or two blue candies. One blue candy or two blue candies. So this is not one. This is one because it's a blue. This is one because that's a blue. This is one because that's two blues. So the question is, like, we could rephrase it. Instead of saying at least one blue candy, we could say, what's the probability? We could also say, what's the probability of her pulling out one blue candy or two blue candies? One blue candy, or two blue candies. So all you would need to do is add 21 plus 21 plus 49. 21 plus 21 plus 49 is going to be 91%. So there's a 91% chance that Jakisha is going to pull at least one blue candy, because that's in these three scenarios. So 91%. Now, math is all about cheat codes and tricks too, right? Math is about a bunch of rules, but it's also about cheat codes and tricks that you can use, right? And shortcuts. So think about it like this. If the question asks at least one blue candy, right? In all of these scenarios, the only scenario where she doesn't pull one blue candy is this one right here, where she pulls no blue candy, right? So another way, since all probabilities have to add up, all probabilities in a situation have to add up to a positive one, you could also say, well, if I know the probability of something not happening, then I could take that probability and subtract it from one. So I could have also said, well, it's a 9% chance that she don't pull at least one blue candy. So that means I could take that percentage and subtract it from one. So I could do 100% minus 9%, which also gives me 91%. So that's just another way to look at a problem, right? So, I mean, either way, you could take the probability of something actually happening and add those probabilities together, 21, 21, and 49, or you could take the probability of something not happening and just subtract that from one. Or like it will be 1 minus 9/100ths, or it will be 100% minus 9%. Either way, you're still going to get the right answer, which is 91%. There's a 91% chance that Jakisha is going to get at least one blue candy. All right. Now, last question. What's the probability of her getting one candy of each color? One candy of each color. So we're not talking about two reds. We're not talking about two blues, right? We're talking about her getting exactly one candy of each color. So a red and a blue and a red. So these two scenarios are the only ones that apply. 21% chance of that happening, 21% chance of that happening. And we said or, right? This or that, this or that. 21% plus 21%, that gives us 42%. So the last answer is 42%. And as I said, the original word problem is typed in the description underneath of the video for you to read. I don't know if you want to copy it down, screenshot it or whatever, right? But anyway, this is like an introduction to probability tree diagrams. I'm telling you, they're very useful. Now, I'm going to do a video also, probably later today, where there's a scenario where there are three selections. So if there are three selections, you'd have one branch, then you'd have two more branches, and then you'd have four more branches, because each of the ends of these branches would each have their own branches. So there'd be another branch and another branch. Like kind of like if we changed this problem up and said, well, what if Jakisha took out 3 pieces of candy? What would be the likelihood of these different things happening, right? We would just put another branch here, another branch here, another branch here, another branch here, right? And then we answer the questions accordingly, you know? So check that out. That's just, probability tree diagrams, just a kind of introduction to that. I want to make sure I said everything that I wanted to say. Yeah, should add up to 1. We talked about that. Replacement, we talked about replacement. Replacement is very important. So with replacement versus without replacement is very key because that affects your response. Why is it called a tree diagram? Well, you can see because tree branches, these represent, or resemble tree branches. And this way, like when you show the tree diagram, what you're doing is you're running through all your potential outcomes. Either red then red, red then blue, blue then red, and blue then blue, right? Those are all your potential outcomes, right? Yeah, so that's about it. Yeah, so that's about it. Remember, and in probability, and means multiply, or means add. And means multiply, or means you adding things up. All right, here go our 4 answers right here. Part A was 9%, part B is 49%, part C was 91%, part D is 42%. If you want the answer as a fraction, you would just say 9 over 100, 49 over 100, 91 over 100, 42 over 100. And 42 over 100, you can reduce that to 21 out of 50 if you wanted to. You know, you can do that. But yeah, I hope you learned something. If you're not subscribed to the channel, please subscribe to the channel. All right. Like this video and share this video with somebody else. All right. So other people can learn as well. All right. Don't hoard the knowledge. Right. Share the knowledge. Pass it on. All right. Also, definitely go practice some more problems like this. So ask your professor, ask your teacher, ask whomever for some more problems, or do a online search for more problems like this, because you got to practice this. All right. You master and become proficient at math by doing practice. You can't just watch the video. That's not enough. All right. You can't just watch the video. Go get some practice. All right. So go get some practice. I'll see you in the next video. Peace.